And hello again. So in the last video, we were talking about something called solid angle. Now, solid angle is this 3D representation of angle. It's meant to help us define some sort of geometry because, well, you can see the one angle only can represent a 2D kind of an effect. Yeah, so it can only give it one angle can only give us a 2D effect, but a solid angle can give us the 3D representation of how something is orientated with respect to each other. One object with respect to another object. So that's the idea. So how can we come up with a general relation for how, let's say, power or the heat flux varies with respect to this angle? Okay, let's start with a few definitions first. So we have something called power emissivity, or rather the correct name is total emissive power. Total emissive power. So now before we start anything, we always want to draw some diagrams to make it easier for us. So I'm gonna cut this out. We already have that. Okay, so we'll have a general stereotypical flat plate. So it's always easier to mathematically start from a flat plate. Alright, let's say per unit area, this area dA is giving out total power output by dA equals to dQ. So the total power output by this small little area here, dA, is this, the power output is dQ. Then, okay, we define the total emissive power equals to dQ divided by dA. Okay, so we start by saying, okay, this little area dA is going to output a arbitrary amount of power dQ, and the power per unit area output by this dA in total equals to dQ over dA. Now, we can't just consider it like that. We can consider the total power output because it's a total emissive power. So that's summing up the power output across all angles. Okay, across all angles it is summed up, and if you want to use what we have learned earlier, this is total emissive power is sum over all angles, or the entire solid angle. Okay, so now let's say we want to be a little more precise with how we define the power. Okay, so I'm going to cut this out. Let's say we want to be more precise. We don't just want the total power output, we want some kind of directionality. Okay, so out of all the so-called rays coming out of this little bit of area dA, okay, I'm going to use a straight line. It's much easier. And 2. I'm only interested in this portion, this little angle. Okay, I'm only interested in this portion. All right, d omega. Okay, so what is the power output that's being received by this representative angle, solid angle d omega? Okay, so let's start with a few things. Okay, let's put this in the Word document. And then we start by typing. Okay, so what is the power received in this small or differential solid angle omega? Okay, or rather I put down there d omega to make it clear. Okay, so we know that this total power output across all solid angles is dq d omega. So total equals to dq, or rather dq dA. All right, that's the total in entirety. So in a sense, you have to sum up. So that's generally speaking an integration across all angles, across all solid angles, and then you kind of have a representative power per solid angle times power, or rather, let's say emissivity per solid angle. Okay, so let's slow down. It can get a bit confusing, but okay. Again, we say that this little dA is putting out a certain amount of power, and the representative total emissivity, the power per unit area for this little guy, all right, is summed up over all angles here, and this is just relating to this. But we want to kind of subdivide it further into this little angle d omega. So we will have a kind of something here. We will have a power, or rather power per unit area. Okay, let me use this. Power per unit area per unit solid angle. Okay, all right, and what will this be? This is something we like to call intensity. Okay, it is something like that. All right, intensity. Okay, so this is something we kind of define intensity. Okay, total. All right. So that's emissivity, or rather intensity. Emissivity per solid angle is so-called our definition of intensity. That is actually I. But wait a minute, we haven't actually accounted for, you know, how this area, this slanting effect, actually affects the amount of power received by this fella, right? Again, we need to take a note of this little cosine, this theta, right? Because when you consider the amount of power falling in this d omega, we have to kind of correct the power per unit area over here, right? So you can imagine here is the most intense, but as you go, increase your theta, here it becomes less intense. Why? Because this little bit of area is not directly facing you. So you kind of have to make that correction. So we'll have to adjust our equation just a tiny bit. but the concept of intensity is more or less there. Okay, so we write, but we need to correct for the angle theta because we are not directly facing the area dA. Alright, I'm gonna snip this over. Okay, just ignore that little box at the corner. Okay, so we need to correct for this angle. And how do we correct for this angle? Well, we have to consider what this little area is. So I'm gonna put this down. What is this area dA? Or rather, let me put it in orange. What is this projected area? What is the projected area? AP or DAP that faces the solid angle head on. So we'll need to make some adjustments. So our total emissivity is as such, but if we correct for angle theta, we have to put an additional cos theta at the bottom. Alright, why? Again, well, if we consider this is the area A, we are facing up. So cos theta is, we can think of it like that, very simply. Cos 90 degrees, or cos 0, equals to 1. Cos of pi by 2 equals to 0. So when we can think of it like this, just the intuition. And don't want to go through all that trigonometry again. But if you want it, you can do the hardcore trigonometry. I'm not going to do it. It's going to take a long time again. Okay, so this is the area A. If it's cos 90, the projected area is 1 times this dA. But if you go all the way here, the projected area is 0. So we can kind of know it's a cosine function. Okay? If you really want, you got to zoom in and then you draw your triangles somewhere here. Okay? You got to draw your triangle somewhere here. This is the right angle, and then theta. Yeah, theta will be here, if you can see. Alright, so you cosine the theta. You can see this little theta I'm drawing here. Then you get this orange area. Okay? Oopsie. Alright. So we have derived a generic expression for intensity. Okay? And now we have also corrected emissivity for the angle theta, so that it works not just at this 90 degrees, but when you go to the side, when you go towards here, you realize that the power you experience is less. It's not because the total emissivity is less. It is because the area projected, the perpendicular area projected to you is less. Therefore, you receive less power. And now we can just have our expression here. Okay, we have our expression here, dq over dA equal, dq over cos theta dA equals to the integral over all solid angles of the I, intensity. So this is how intensity is kind of defined. I equals to d by d omega, or rather I do a partial. Oh no, I just put a d by d omega of this whole thing. Okay, nothing more than that. So the basic idea is, if I want the amount of power coming into this small little solid angle, then I can just I have to correct for this theta, and I consider this solid angle, and that will be I. So again, I'm taking the total emissivity, the power per unit area, dA, dQ by dA. So that's the emissivity. But the intensity contributed to by this small little box is just, well, you have to subdivide it into the various solid angles. Okay? So this is how we start our two-plate problem. Okay, so in this video we define what intensity is. So in the following video we can actually start with our little two-plate problem and try and calculate a little more about our, we can try and calculate our view factor. So these are the general concepts we need to know before we start on the view factor. Thanks for watching.